Hey everybody, this is your favorite stats prof. I'm assuming I'm your favorite stats prof. I'm assuming I'm your only stats prof, so that makes me your favorite one. It also makes me your least favorite one, so I guess there's that. Because this last class this week is going to be pretty crowded with some new stuff, I thought I'd record some of it online so that you don't have to sit there and listen to me in class too much. And I thought I'd record the review session online. And so if you're watching this before attending the last class, there's going to be some stuff that I'm reviewing that you haven't seen yet, because we'll see it in the last class. So wow, let's see what I want you to take away from this course. First, the final exam is not cumulative. That means we'll only cover things since the midterm. So what have we done since the midterm? In other words, what have we done that is testable on the final exam? Well, we've done one-way ANOVA, in the sense that you know how to compute a one-way ANOVA. You know when to use a two-way and an n-way ANOVA, but you know how to compute a one-way ANOVA, or ANOVA, as the kids say. You know how to do a chi-square. You will know, as of the final class, what a ranked correlation is. And a ranked correlation uses Spearman's rho, not Pearson's rho, Spearman's rho. You will have learned how to do linear regression, which should be a high school review. But if not, you'll learn all afresh in the last class. And basic sample size calculation, which is what we covered in last week's video. We also learned, but we didn't do by hand, we learned the variations of the chi-square, the McNemar's test, and Yates correction and things like that. But we didn't learn how to compute it, but I want you to know what they are and when to use them. We also learned what a two-way and an n-way ANOVA is, but again, we won't be computing those. I just want you to know when to use them and what they are. And we will have also learned what multiple regression is. We will not be doing multiple regression computations. It's way too hard, but I want you to know what it is and when we would use it. So let's go over the ANOVA first, the analysis of variance. Essentially, the analysis of variance tests whether the means of different groups are the same or different, whether the mean mileage of this group of cars is the same as that group of cars, is the same as that group of cars. It's like a t-test, but a t-test only compares two groups, and ANOVA compare lots of groups. So we can do a one-way, a two-way, or an n-way, and that depends on the number of categorical variables that we have. So in this class, we only learned how to do a one-way ANOVA, but again, I want you to know what the two-way and the n-way are and when to use them. So, if we are comparing the mean bacterial count in 4 samples of milk, how many categorical variables are there? Only one, milk, right? Samples of milk is my one variable. That's a one-way. Comparing the mean weight of men versus women among Canadians versus Americans, how many categorical variables are there? How many independent variables are there? Independent variables are there. The categorical variables. Well, there's 2 of them. There's the gender, the men versus women, and then there's nationality, Canadians versus Americans. 2 variables. That would be a two-way. And comparing the mean price of 6 categories of vegetables in 4 different grocery stores in 7 countries. All right, we got vegetables, categories of vegetables. We've got the different grocery stores, and we've got different countries. That's 3 different categories. That's going to be an n-way. That's how that works, children. So the independent variable, I said again, is the number of, it's the categorical variables. It's what you are independent to be in, right? You can be in a different ethnic group, different genders, different nationalities, etc. But your score is dependent on which category you are in. So again, the independent variable in ANOVAs are categorical or nominal, sometimes ordinal, but the dependent one is going to be the continuous variable, the thing that we're computing means on. The thing about ANOVA that makes us special is we have two kinds of variances we have to compute. We've got the between group variance, and we have the within group variance. So if I'm comparing the mileage of cars, different samples of cars, then within each group of cars, each car is going to be a little bit different. They're going to vary. That's my within group variance. And between the groups, there's going to be variation as well, different makes of car perhaps. So I need to account for both of those sources of variation. And to do so, we compute something called the F ratio or the F statistic. That's the thing that eventually gets plotted in our distributions. And the F is essentially the between group variance divided by the within group variance. Like with all of these parametric tests, we need to compute a degrees of freedom computation that allows us to look up the appropriate cutoff point in the back of the book. So with ANOVA, we need 2 degrees of freedom. We need the between group degrees of freedom, and we need the within group degrees of freedom. So that's going to be computed in these ways. The between group degrees of freedom is the total number of nominal categories minus 1. So if I've got 4 makes of car, that's 3. My degrees of freedom there is 3. Within the group, that's going to be the total number of things in my group minus the number of groups or categories. So if I've got 3 groups of cars and each one's got 5 cars, that's a total of 15 cars. And I'm going to minus the number of groups, so 3. So 15 cars minus 3, 12. There you go. And that's summarized in the green. So to compute the ANOVA, essentially you have to compute something called the sum of squares. The sum of squares within each of these groups and the sum of squares between all of these groups. And once I do a ratio, the sum of squares between divided by degrees of freedom, all of that divided by sum of squares within divided by degrees of freedom, that ratio is the F ratio. And what do I do with that F ratio? I compare it to the back of the book. But of course, before I do that, I need a null hypothesis. And the null for ANOVA is always that all of my categories are the same. The alternative, of course, is that all of the categories are not the same. So in other words, one of them is different, or 2 of them are different, or all 3 of them are different. I don't know. I just know that if my null is not retained, something's not the same. Why is my slide not progressing? There we go. Come on, slide, progress. Okay, now that's chi-square. The chi-square tests whether 2 categorical variables are related. So far we've looked at ANOVA, which compares continuous variables. Now we're looking at chi-square, which compares categorical variables. The examples we did in class are customer satisfaction related to, the employee satisfaction. I can do is gender related to, I don't know, smoking status. Anything in which there are categories, I can do a contingency table and compute a chi-square. Now, if my categories are not nominal, I have other options. So if they are ordinal, well, I use a Mann-Whitney U test. What's an ordinal measure? Well, that would be something like a Likert scale. How much do you like this class? A lot, a little, or not at all. That's a 3-ranked ordinal scale. For that one, I would use a Mann-Whitney U test if I've got 2 groups. If I've got 3 or more, I'd use something called a Kruskal-Wallis test. But if they're all nominal, I'd use the chi-square. So the thing about a chi-square is that it's essentially testing whether or not the categories have proportions that are equal. What does that mean? Well, imagine the contingency table again. Imagine looking again at gender and smoking status. So is the state of smoking different between men and women? And I'm measuring smoking in terms of yes or no. So is the proportion of smokers in the women different from the proportion of smokers in the men? My null says that the proportion are going to be the same between the 2. And the alternative says that they are not going to be the same. So to do a chi-square, we create a contingency table that shows all of the possible contingencies. The women who smoke, the women who don't smoke, the men who smoke, the men who don't smoke, etc. And we compute the expected values from the observed values. Again, observed and expected, that's an important distinction in statistics. Like, we come back to that a lot. The observed values are our data. That's what we have in our sample. That's what we observe. What we expected, if the null were true, if things were random, are essentially the marginals divided by the total. And the marginals, again, are the totals at the end of the rows and the columns multiplied by each other, divided by the total. If things were truly random, then the marginals would give us the expected values. And we're going to see if the expected and the observed are so close enough that maybe we can say nothing's going on, or the null hypothesis is true. We also have to compute degrees of freedom, as we always do for all of these ridiculous tests. So with the chi-square, we assume that there's a random sampling of observations. We assume that just because the first person smoked doesn't mean the second one's going to smoke, etc. But more importantly, we assume that nothing is expected to be 0. Okay? And nothing is observed to be less than 5. 5 is our cutoff. If it's less than 5, the chi-square computation that we do in class will not be valid. And this is our formula. We take the observed minus the expected divided by expected square, and you add them all up. But you got that from your notes. And from the chi-square, to compute the degrees of freedom, we use this formula. Rows minus 1 times columns minus 1. So what do? We state our null that says nothing's going on. Gender is not related to smoking status. Patient satisfaction, customer satisfaction is not related to employee behavior, whatever it might be. We create our contingency table. We fill in our numbers. We compute the expected frequencies. Check our assumptions. Make sure that the expected frequencies are not 0. The observed are not less than 5. We compute our chi-square and our degrees of freedom. And we assess the null by comparing our chi-square to the number we look up in the back of the book. We want our number to be bigger than the book's number because that allows us to reject the null, because we love to reject the null. Yay! Null rejected. We also will have looked at ranked correlation. And again, if you're watching this video before the final class, you will not have looked at rank correlation yet. But rank correlation is what we'll cover in the final class. And rank correlation is simply seeing if two ordinal variables are related. What's an ordinal variable? A rank. Is your preference in ice cream flavors related to your rank in how well you do in stats class? It shouldn't be, but it might be. Here, this example shows whether or not thievery is related to preference in ice cream, and it's confounded by the fact that more theft occurs on hot days during which you're more likely to eat ice cream. It's a stupid picture, don't worry about it. So, ranked correlation tests whether or not two ordinal variables are related. We did earlier in the year Pearson's correlation coefficient. Pearson's correlation coefficient measured whether two continuous variables, interval ratio, were related. But Spearman's correlation tests whether or not ordinal or ranked variables are related. And essentially, Spearman's rank is a Pearson test on ranked data. That's all it is. We also call this a rank order coefficient. Now, I want you to know that with Pearson's test, which is the test of continuous variables, you're essentially saying, is there a straight line? Is there a linear relationship? Meaning, as one goes up, does the other go up the same amount? Whereas Spearman's row, which tests for the ordinal ranked relationship, tests for what's called a monotonic relationship. A monotonic relationship says as one goes up, the other goes up, but not at the same amount necessarily. It can go up a little bit, next one goes up a lot, next one goes up a little bit again. So it's always going up, it's just kind of right? Whereas Pearson tests for linearity, Spearman's test for it's going up. Okay, here's some examples. Are these ranked or unranked scenarios? If we are correlating people's preferences in ice cream flavors with a calorie count, well, once you've got preferences, you're looking at ranking, so that's going to be ranked. Correlating children's age and height. Is a ranking happening there? Age is a continuous variable. Height is a continuous variable. We're not looking at which kid is ranked higher or not. We're looking at which one's ages are higher. So that's not ranked. Property tax with the number of rooms in a house. This one's odd because property tax is a continuous variable and number of rooms in a house is an ordinal variable, but it's a weird kind of ordinal variable in which the difference between 1 room and 2 rooms is the same as the difference between 2 rooms and 3 rooms, which is the same as between 4 and 5. Rooms is a set unit difference. So in truth, we could actually do both. We could do a ranked or an unranked test here. Technically, it is ranked, technically, but I'd accept either one. Your favorite world cities with average temperatures. So if you're ranking, I prefer London over Paris over Toronto, and I want to see if that correlates to temperature. Maybe I actually like warmer countries and cooler ones. Well, once I've got preference, that's a rank. So that's going to be rankedness. This is the formula for computing Spearman's row. It is a 1 minus 6 times the sum of the differences in rank. And again, in class, we will go over, or have gone over, how to compute that. And as with all these things, there is a degrees of freedom. And this is the total number of things I have in my data minus 2. So we get that. Okay. And much like Pearson's row, we interpret Spearman's row in the same way. It goes from -1 to +1, closer to 1, the more perfect a correlation. And if it's a positive direction, it's a positive correlation. If it's a negative number, it's a negative correlation. Then we will have looked at linear regression, which is related to correlation. Because correlation is really looking to see if you have a linear relationship. So we do linear regression to make predictions. I can regress the relationship between your midterm mark and your final mark. And I can use that relationship to test the next year's class. So next year, I'll look at all the midterms I got, and using this year's class, I'll predict what their final work would be. So linear regression essentially is using sample data of 2 continuous variables to create a model that allows me to predict future behavior of other people's continuous variables. But I need 2 continuous variables, one predicting the other. So it is, we are modeling a linear relationship between 2 variables for the purposes of making a prediction. To do so, we have a bunch of numbers for x, and we try to figure out the best values to create our straight line equation, which is y equals a plus bx. So we have a bunch of points on our scatter plot. Which straight line equation best fits that plot? If you remember your high school mathematics, you remember that the straight line equation is y equals mx plus b. Well, we write it similarly, but a bit different. We say y equals a plus bx. So m, your slope, is now b, your intercept. B, your coefficient there, and a is the intercept, right? So it's just y equals mx plus b, but now we say y equals a plus bx. Same kind of thing. We have this thing called y prime, though. So once we have created our straight line, y prime is what we now predict. Let me go back and explain that again. So this is the data that describes a straight line, and this is the sentence that describes the model that I've just made, where x is my real data and y prime is what I'm predicting given x. The slope b is now called a regression coefficient. The slope is critical to this process. What we're really doing here is this. So here in red, those D3s and D2s and D4s, those are the points. Those are the points on my graph, my actual data. And that straight line that runs through it, that's the best fit of a straight line. How did I get that best fit? Well, I dropped a straight line from each of those points to a billion different possible lines along that y-axis. All those drops were like down the y-axis. And I figured out which line gives me the least total average length of those vertical lines, right? So if you recall from earlier in the year, if we've got things that are negative and things that are positive, and we want to figure out what their magnitude is, an easy way to do so is to just square them. You take the square, the minus sign goes away, and then we can work on just magnitudes. That's what's happening here. The points that are above my line are positive, the points that are below my line are negative. If I square those values, then the minus signs go away, and I figure out which line gives me the least value for all the sum squares. That's what this is, the least squares method. It minimizes the total magnitude of those least squares. So what I'm really doing here when I make my linear model is I've created a straight line equation with some error. The error is what we call the residual. The residual really is how much my prediction varies from the actual point. If I go back for a second, once I draw my line here, clearly it's a pretty good straight line, but it's not precise. It doesn't go through all these points. That's an error. That's an error. That's an error, etc. Each of those is a residual. The difference between the point and the actual line, that's a residual. The error term is not a constant. As you see here, if it was a constant, each of these lines would be the same length. They're not. So these errors are the actual y value minus the predicted y value. So we can compute a standard error of the estimate using that information. The standard error of the estimate is the sum of all the residuals squared divided by n minus 2 under the root sign. And with that, we can compute a t statistic. Why? Why would I do that? Why would I want to do that? Because it's one thing to create a straight line equation, which is fantastic for making predictions, but we also want to know whether or not it's a good straight line. And one way to do so is to compute this t here and use the degrees of freedom and look up at the back of the book to do what? To test a null hypothesis. What's the null hypothesis? That our slope is 0. So if I look up in the back of the book and I find that this is not significant, that means that I retain the null and I say my slope is 0, which means my line is not particularly useful. But if I can reject the null, then the slope is not 0 and my line probably is useful. Now, there is a relationship between correlation and regression. What kind of correlation? The Pearson correlation, the one we did in the beginning of the year, the one that looks at straight line relationships. And that relationship is this. If I square the correlation value between two continuous variables, that's the same as that formula here that I got from my straight line. In other words, if I do a linear regression, I can take that information and compute a Pearson's row from it as well. The last thing in the year that we will have covered is this thing called multiple regression, which is probably one of the most useful multivariable tests that you will ever come across in your data analysis and health sciences careers. And it's this. I said that I can predict your final exam mark based upon your midterm mark because in previous years I've run linear regressions to do so. I looked at previous years' relationships between their midterm and their final, and I created a model. But what determines your final mark isn't just your midterm mark. It's also, I don't know, your age, your height, let's say, your IQ, all those factors. So if I've got a bunch of continuous variables that add to the soup to make my prediction, I can combine them all using multiple regression. And so my final estimate of your final exam mark is based on a series of linear combinations of continuous variables. So this x1 here, maybe that's how you did on the midterm. x2, maybe that's how you did on the lab exams. x3, maybe that's your IQ. x4, maybe that's your, I don't know, your income, whatever it might be. And I combine them all to get a solid sentence mathematical formula for accurately predicting how well you will do. Magic! Now, remember that with a correlation, a simple correlation, and with a straight line equation, we could compute a small r, Pearson's rho. We call that the correlation coefficient. And we said, if you cast your mind back, we said that small r squared describes the percent of variation that one variable explains in the other. We also said that it ranged from -1 to +1, where 1 shows a perfect relationship. Well, capital R works the same way. So capital R tells us how well all of those variables I threw into my multiple regression soup predict the outcome that I care about, in this case, your final exam mark. But capital R is different from small r because there's no negative values. It only goes from 0 to 1, and 1, of course, means a perfect relationship as well. We also talked about sample size calculation. Now you learned that you need to know some characteristics about your population and your study in order to compute sample size. And I gave you a couple of formulas. And I said, if we fix our type 1 error at 5%, and we're looking at a two-tailed test, and we fix our power requirement at 80%, then if you only need one group, if you're testing for blood pressure changes from to you need this number of people. H times the variance in your sample divided by the square of the difference that you're trying to detect, approximately. However, we also said that if you needed two groups, then this is the formula you use. It's 16, it's twice as big as the previous one, but you need that per group, so it's 4 times as big as the previous one. So, after all that, what do I want from you? I want you intellectually to be able now to know which statistical tests you would use in certain characteristics, because you learned a lot of tests. You learned a lot of tests, my friends. So if we're comparing the mean IQ of men versus women among nursing students versus HSS students, okay, what are we doing there? Mean IQ, that's a continuous variable. But now we've got two categorical variables, men versus women and nursing versus HSS. So that's going to be an ANOVA. What kind of ANOVA? A two-way ANOVA. Da-da-da-da. We're comparing the mean blood pressure between 5 ethnicities. All right, that's going to be an ANOVA as well, because mean blood pressure. But how many categorical variables do we have here? Well, 1, ethnicity. See, it's not 5, it's only 1. There's only one variable there. So one-way ANOVA. If we are predicting the final weight loss of the contestants of season 11 of The Biggest Loser based upon their starting weights, what's that all about? Well, anytime we're predicting, we're building a model. We're regressing. So this is going to be a linear regression. Is there a relationship between which faculty and which students are enrolled and by which means of transportation they use? Ooh. Well, the way we do this kind of thing is look at what kind of variables these are. So which faculty and which students are enrolled? That's nominal. Health sciences, medicine, whatever. Which means of transportation? Well, that's nominal too. Bus, bicycle, walk. 2 nominal variables, that's a chi-square. Predicting the sex ratio of a nation of Bangladesh. Okay, prediction. So automatically you know it's regression based upon values of total base population in each year. Okay, so it's going to be a regression. The question is, what kind of regression? Well, you've got several predicting variables here. You've got base population of each year the past decade. That's 10. 10 continuous variables predicting 1. That's a multiple regression, my friends. Is there a relationship between the number of hours students spend watching TV and their relative standing in stats class? Okay, so what kind of variables are these? Number of hours students spend watching TV is continuous. Relative standing, that's ordinal. That's a rank. That's a giveaway, right? So we're comparing a ranked variable to something else. That's going to be ranked coefficient. So a Spearman's rho. Ranked correlation. So your final exam is going to be on December 14th, late in the evening. I'm not happy about that either. Don't blame me. I don't schedule this stuff in wherever that room is. What is that, Marion? I don't know what that is. And the exam looks like this, I think. I haven't fully made it yet, but it will look like this. So again, only the things that we've done since the midterm. The ANOVA, chi-square, Spearman's row, regression, and sample size. Okay. It says here, calculation questions will be similar to your second data analysis. You guys didn't do a data analysis assignment this year, so ignore this. It will be similar to what you have done already in class in your homework. So, in the theory stuff we've learned since the midterm are things like type 1 and type 2 error. So, this stuff we learned, you back up, Ray, back up. This slide shows us the things I expect you to calculate. Now, the exam is not just about calculation, it's about theory stuff too. All of the theory we've learned since the midterm is fair game. In addition, I want you to know this theory from the first half of the class. Type 1 and type 2 error, what a null and alternate hypotheses are, and how to use p-values. Those three things never go away. So I will test you on those as well. Okay, what's the format? As always, all multiple choice because this is health sciences and we are lazy. Exactly half computations and half theory. In previous years, it was pretty long. I'll probably knock off some questions this year to make it shorter. What does that say about you? What does that say about you that I feel the need to knock off questions? That's not a good thing, but I will. What to bring? As always, you get a cheat sheet. That should say 9.5 inches, whatever, a regular sheet. You can write or print on both sides. I don't care. Bring a calculator. I will not give you equations. You bring your own equations. But you do not need to bring the chi-square tables and the ANOVA F Statistic tables from the back of the book. I will give you those. Okay, so don't worry about that. That is all, my friends. Good luck. It really ain't that hard. It ain't that hard. We'll see you on the 14th.